so start going through this. So welcome. Yeah, so everyone now on YouTube, I'm gonna we're gonna do a review of the entire sort of semester by going through a bunch of questions. So again, if you're watching this live, you can stop and ask me for clarifications or questions at any point. Let me make sure just the YouTube is working. My internet's been a little funky today. We're gonna do a review. Yeah. Okay. Great. Of the. Okay, so you don't need to hear me twice. Okay. So we're gonna start, and this will be a coverage of all the material in class. And so we start with probability. And so the first question here was consider random variables, X and Y, and we ascribe them with this probability table, right? So if you remember this, I can ask now a bunch of questions about these random variables. For instance, what is the probability of X equals 1? Probability of X equals 1 corresponds with this column. And so this probability table kind of writes down all these joint probabilities. And so the answer here, I would add these two things up, 0.40. So this is 0.4. Okay, if X, and then the next question is if X equals 2 and Y equals 1, right? So that looks like a single cell inside of here. So this would be equals 0.05. Right? And then the next one is if X equals 3, given that Y is equal to 2. Right? So now we're restricting to this column, and we're particularly interested in X equals 3. Right? So in order to do this one, we need to kind of just look at the aspect within this column. So the first thing we would do was add all these terms up. This is 0.75, that Y is equal to 2. And so the answer here is the probability that's 0.2 divided by 0.75. Okay, that's the conditional probability of X equals 3, given that we know Y is equal to 2. Okay, and then we're going to compute the following probability distributions. What is the marginal distribution for X? Okay, so that's saying when you marginalize out, you get rid of the effect of Y. So we're writing the marginal distribution for X. So for X equals 1, I added these up. I've already done this for this first one, 0.4, right? For X equals 2, it's 0.25, and for X equals 3, that's 0.3. So I would probably, if I was just writing this out on paper, I would write this as a table, X equals 2, X equals 3, and that's 0.4, 0.25, 0.3. Oh, there's a mistake here. This should be 0.3. Okay. One of the ways you can check this is that these should add up to 1, right? So if I add these terms up, right, the sum here should be equal to 1, right? So I made a mistake, right, but it allowed me to kind of illustrate that you can use these properties to check what's going on. Okay, what's the conditional probability for Y given that X is equal to 2? All right, so now the conditional probability for Y given that X is equal to 2, this is again going to be a table, and this is going to correspond with this conditional probability that X is equal to 2. So now I'm going to write this as another table, Y equals 1, Y equals 2, right? And so it's going to be 0.05 divided by 0.3 and 0.25 divided by 0.3. Okay, and so I could work out these probabilities, and they should add up to 1. But if I have two parts, 0.05 and 0.25 that I know add up to 0.3, then I divide through them both by that. Each I know they're going to add up to 1. They have to do that based on this construction. So that would be the answer here. Okay. Okay, are random variables x and y independent from each other? Okay, independence is a really important concept in class. Are the random variables independent from each other? We're looking at random variables now. For this to be true, it has to be true for all kind of possible events at the combination, and that's not going to be true in general here. Okay, so random variables x1 and if I look at x1 and y1, these should be the same independent, basically x1 so I should be able to look at any two events, and so I should, yeah. So there are a few ways of doing this. Let me just review that kind of a random variables x and y are independent if all kind of so events, let's say a in x and y and b in y are independent. Okay, and so I can look at the event. So one thing I can check is if let's look at this one case here. I can say the probability that I've calculated, the probability that x equals 2 and y equals 2 should be equal to the probability that x is equal to 2 times the probability that y is equal to 2, right? So I picked these because I calculated them. The probability y is equal to 2 is going to be 0.75. The probability x is equal to 2 is going to be 0.3, and the probability they're both true is 0.25. Okay, these are not equal to each other. Okay, so if I can find any event where they're not equal to each other, then the answer here is no. Okay, and for these events, x equals 2 and y equals 2, these events are not independent from each other. Okay, now the tricky thing is events, x equals 1 and y equals 1, these could be independent from each other, right? If I write this out, now the probability that x is equal to 1 is going to be equal to 0.4. The probability that y is equal to 1, okay, this is going to be equal to 0.25. And the probability that x equals to 1 and y is equal to 1, okay, that should be the product of these two things. That should be 0.1. And if we go and look, that's true, okay? So the answer here is yes. Okay, so the events are independent, even though the random variables are not independent, because the random variables need all possible events to be independent for them to be independent. Okay, so these are kind of some tricky aspects about independence and probability. Okay, any questions here?
There was a question on the chat that if it is going to be recorded or not. I said yes.
Yeah, that's right. It's currently live streaming on YouTube and it will be up. Yeah. Okay, great. Yeah, these are also questions in my book, so I'm going to take it down after the semester. So classes elsewhere, or their versions of these are in the book. But okay, consider two models, but it will be up through then the exam for sure. Okay, consider two models, M1 and M2, where the prior knowledge we believe M1 probability that is 0.0 is 0.25. Probably M2 is 0.75. right? Then we observe some data D. Given each model, we assess the likelihood of seeing that data given the model is let's see, of data given M1 is 0.5 and data given M2 is 0.1. Okay, so the model 2 does a much worse job of is less associated with the data. If we assume model 2, then the data was much less likely to happen, right? That's kind of what this is saying. But we had priors, which was the opposite. The prior was that model 2 was more likely before we saw the data, effectively. Now we have the data. We want to know which model has higher probability of being correct. We have discrete probabilities here, so we can calculate everything. And remember, we just need to compare the probabilities. So the probability of model 1 given the data, okay, is going to be proportional to, or let's say is exactly equal to, the probability of the data given model 1 times the prior of model 1 divided by the probability of the data, right? But we don't really know what the probability of the data is. So we can say this is proportional to, it's some constant, times the probability of the data given model 1 times the probability of model 1. Okay, and so this is proportional to kind of the probability of the data given model 1 is 0.5 times probability of model 1 is 0.25. Okay, and this is proportional to 0.125. Okay, and I can do the same thing for probability of model 2 given the data. Okay, this is going to be, well, it's proportional to, I'm taking out the same constant factor, so I'll be able to compare them. Okay, the probability of the data given model 2 times the probability of model 2, and this is, or is proportional to, this is now 0.01 times 0.75. So the model is more likely, but the observation of the data makes it less likely. So this I'm going to get down to 0.075, and this is less likely. I can compare these. There's the same factor. I've factored out the same term here from both of them, right? So I can still compare these with each other, even though I don't know the exact probabilities. And I can say that this one is larger, right? Because 0.125 is bigger than 0.075. Oh, yeah, there's an extra 0 here, as Hassan is pointing out. Thanks. Great. It's still smaller. Okay, great. So this is an application of Bayes' rule. Again, Bayes' rule is an important thing that you'll probably want to know on the exam. Okay, let's see. Okay, so now, okay, question 3. Assume I observe 3 data points, x1, x2, x3, draw an ID from an unknown distribution. Given a model M, I can calculate the likelihood that each data point as probability of x1 given the model is here, probably x2 given the model is 0.1, and probably of x3 given the model is 0.2. What is the likelihood of seeing all the data that's so given the model? Okay, so the key thing here, the key thing to identify here is that these are IID, and these means they are the key part of this is the independence. The independence allows me to say that x1, x2, x3 given the model is going to be equal to the product of x1 given the model times probability of x2 given the model times the probability of x3 given the model. So I can take the joint probability, because of independence, is going to be the product of the three things. And then I can just write these out: 0.5, 0.1, and 0.2. Okay, and I can leave it in this form if I want to, or I can multiply them out and hopefully I get them so correct this time. It's going to be, let's see, 0.0 0.1. Yeah, okay, good. Right, so that's the answer. But if you get something like this, you can leave it as the factored form. If you're writing on the final exam, write it out, and it often makes sense to look at it to see if it makes sense in your mind. But if you write out your work, you will get it correct. No, is that not right?
Just 1 0, not 2 zeros.
Oh, okay. Yeah, okay, good. See, I would have still given myself full credit on that one because it was a numerical mistake, but yeah, but you should check. Okay, if you write out your work, you can still get full credit if you make a numerical mistake like that. Okay, but the key thing here is independence allows that the probability to be taken as the product, right? And this came up a lot in all of the models we have. This things you can factor stuff as product was really important, and then you can take the log and you get a sum of these independent terms, right? This is kind of essential to all of these kind of these decomposable models and everything like this. Okay, will all questions have a text box, or is it mixed format of questions? Yeah, so this year on the final exam, I'm leaning towards having trying to not have too many of the text boxes, and I think that will allow me to ask a few more questions because they'll be simpler to answers. There'll be things like multiple choice and true false and matching and stuff. There'll be some with text boxes, but that'll allow me to assign smaller amount of credit for each, and then you'll be penalized less for getting any one of them wrong. So that's my plan so far. Okay, but there'll be some text boxes. Okay, but if you have text boxes, feel free to write as much as you want. And if it doesn't match, we'll have some automated answering sort of stuff. If it doesn't match that, then we'll go through afterwards and make sure the right answer is assigned. So don't worry. If you fill in your work, we'll go in and check everything afterwards. Great. So consider a PDF for F so that a random variable X has expected value. Okay, expected value 3 and variance of 10. Now consider n IED random variables x1 through x10 drawn from F. Let x bar equals the average of them. And we want to calculate a bunch of these things. Okay, so this is a central limit theorem question, right? So this is about the central limit theorem. And what we know is on the average, we preserve the expected value. So this will be exactly 3. And the variance gets divided. This is going to be var of x gets divided by the number as 10. So this used to be 10, and now this is going to be equal to 1 when we talk about that average thing, because the variance gets smaller as we average more things together. Okay, what is the standard deviation of x bar? Standard deviation is equal to the square root of the variance of x bar, right? And the square root of 1 is equal to 1. Okay. Okay, now for some of the more thinking questions. Is the probability, which is larger, the probability of x greater than 4 or the probability x bar is greater than 4? Okay, so what's going on here, you should try and draw a picture Okay, we should say that the expected value of x bar is equal to 3, and x is equal to 3. Those are the same. Okay, and we're going to have one distribution for, actually, let me draw this again. We're going to have some distribution for, that looked horrible. Okay, this is the distribution for, we don't know what the distribution is, but this is the distribution for x. This is f of x, and the variance here is, or the square, or the standard deviation is about square root of 10. Okay, that's about the standard deviation for 1, and for x bar, it's going to be a much narrower distribution. X bar here, and the standard deviation here is going to be about 1. It's going to have the same expected value, but much narrower distribution. And so now the question is asking, let's look at the probability that it's greater than 4, right? So the probability that x is greater than 4 and probability that x bar is greater than 4. For x bar, it's going to be this region, and for x, it's going to be this bigger region, right? X has more of a tail, and so we have to assess, is this talking about the tail or is this not talking about the tail? And we're talking about the tail. The tail is bigger here, okay? So we can say that the probability of x greater than 4, right, is this light blue region is going to be greater than the probability, that's, the probability that x bar is greater than 4. This corresponds with this little pink region in here. Okay? Now so that's going to be this question. For the next question, which is greater, x greater than 2 or let's see what I want. Or x bar greater than 2. So now we're looking at the other side. We're looking in this direction. Okay. So now you can kind of look at it's kind of the negative of the previous question. Oh, how do you come up with the heights for f of x and x bar? Oh, okay. So, well, I don't know what the exact heights are, but I know that x bar is more concentrated. Okay, so these are both random variables. They're both probability distributions. So they both have to integrate to 1, but x bar needs to be skinnier, right? The standard deviation is smaller. That's what I know from the central limit theorem. That's more concentrated. Okay, I don't know exactly what it is, but I know it's more concentrated. And so so it has to have more mass close to the expected value. And so then if I look at the tail, I know the tail there's more stuff in the tail for x than there is for x bar. And that's what the first question is asking. The second question, E, is asking kind of the opposite, right? Now I want to count the stuff that is not in the tail on the other side, right? So now for this one, x bar is going to be bigger because it's going to include kind of almost the whole distribution here, whereas in the case of x, yeah, they both total add up to 1, but it's missing out. Kind of the problem is you can't see that it's missing all of this. All right, so x is missing all this stuff over here, where there's pretty little stuff from x bar that was missing. Right, I say greater than 2. Okay, so for D, x is greater than x4. For E, x bar greater than 2 is bigger. Okay, yeah. So this is kind of makes you think about the central limit theorem a little bit. This is kind of a trickier question. Okay. Okay, great. Question 5. Okay. Let x be a random variable that you know is in the range of -1, 2, and you know his expected value of x0, use the Markov inequality to upper bound x greater than 1.5. Okay, so this is, I know this is a Markov inequality question. I have x equals 0 here. And there's a hint that I need to change variables, right? Yeah. Yeah. So I know this is gonna. So I need to change variables for Markov inequality. I needed a random variable that is strictly greater than 0, but that's not what I have up here. Okay, so I'm going to write a new random variable. Y is going to be equal to x plus 1. Okay, and I'm just taking a probability distribution. I'm adding 1 to it, so I can do that. And now I'm going to have a random variable from 0 to, let's say, 4, and this is 3, 2, and 1, and this is the value of y, and it's going to have some value here, but afterwards it's 0. Okay, so this is what I know about this value y. It's now between 0 and 3 because if I were to extend this backwards, yeah, so this is the value for y. If I did the same thing for x, it would be pretty much the same thing up to -1. Okay, there's something, and I've shifted it right. It should be the same thing, but shifted, but those are different. I don't know, I just know the range here. But now that I have y, I can answer this question. I want to know the probability that x is greater than 1.5, which is equal to the probability that y is greater than 2.5. Okay, so now we can answer this question. These are equivalent. I've added 1 to both sides of this inequality, right? I've basically done a plus 1 and a plus 1 on both sides, and that's how I get this inequality. And now I can use the Markov inequality, to say that this is less than the expected value of y divided by 2.5, because now y is strictly greater than 0. I know that. Okay, and the expected value of y is the expected value of x plus 1, right? So this is going to be equal to the expected value of x plus 1 by linearity of expectation. I can factor out this. Right, I can take this guy and I can take the expected value of y. I know the expected value of y is equal to the expected value of x plus 1 is equal to the expected value of x plus 1 outside the expectation, right? And so this divided by 2.5. And now the expected value is going to be equal to 0 plus 1 divided by 2.5 is 1 over 2.5. Okay? And I can leave it in this form. 1 divided by 2.5 is going to be what is that, like 0.4? Right? So, okay. Right. Yeah. So its answer is 0.4. So the probability that x is greater than 1.5 is less than or equal to 0.4. Okay, cool. So there's a Markov inequality, change of variables, linearity of expectation. These are kind of the important properties here. Okay, so on to some stuff from linear algebra. Okay, we have a matrix shown here. Add a column to A so it is invertible. Okay, so if it is invertible, it needs to be square. It has to be so full rank. Okay, so I need to be square and full rank. And And so I'm telling you, then the rank has to be this saying is implicitly the rank has to be 3, and I need to make it so it's linearly independent of any of the previous columns. Okay, so I can just add any column here that's going to be linearly independent of these previous ones. So I can do 2, say -2, -3, 100 or 1017. Okay, this is pretty different from the other ones. It matches the first column up to something, and then it's fairly different, and that means it's going to be pretty hard to get from that one. You'd probably want to have some way to kind of check this, and this is kind of trickier to do on a final exam. So it might be hard for me to ask a question like this, because if you added something that was accidentally linearly dependent, that'd be kind of tricky to find. But in general, if you add another column, then it's going to be square, and hopefully it's full rank. Okay. Okay. Now for B, I need to remove a row from A, so it's invertible. So the same thing. It's 4 by 3. I need to make it 3 by 3, right? And so I need to figure out if there's one row which can be made from another row, then I definitely need to remove that one, right? It could be I can remove any row, but turns out there's 2 rows which are going to be where one is going to be was supposed to be a scalar multiple of the other one. I'd intended for this question to have a 4.5 here. So then these 2 rows were scalar multiples of each other. So they're linearly dependent if I have that 4.5 there. And if I can multiply 1 by -1.5 and I get the other one, in that case, I need to remove one of those 2 rows. But in this case, all the rows are, if I removed any row without that added 0.5 there, then I would need to remove just any of the rows would have worked. But if I have this added 0.5 there, then I have to remove one of those 2 green rows. Otherwise, they're not all linearly independent of each other. Okay. Now, this next question, is A transpose going to be invertible? Okay, so it needs to be square and full rank. So A transpose is going to, A is 4 by 3. So A transpose is going to be 4 by 4. Okay, but the rank of something, if I take the product of 2 true matrices, the rank is no more than the rank of the matrix with the smallest rank. So the rank here is not more than 3. So the rank of A transpose is going to be less or equal to the rank of A, or the min of rank of A and rank of A transpose, which is the same. So it's less or equal to 3. So it's not full rank. So the answer here is no. Okay. And if you're doing this so where you had access to a computer, which you won't on the final exam, you could verify that A transpose is going to be is a 3 by 3 matrix, and its rank is still going to be 3. So it's going to be full rank, so it's invertible. So the answer here is going to be yes. Okay, so A transpose A is invertible, but A transpose is not, because it's not full rank. Okay. Okay, so these, inversion, this usually is how inversion happens when you're doing day analysis, when you multiply a matrix by itself to get a square matrix, and then that's usually what you want to invert. And you want to make sure that it is going to be the smaller ranked version of this, otherwise you won't be able to invert it. That's kind of the main thing to kind of take away from this one. Okay. Okay, more linear algebra. Consider 2 vectors, u and v. Check if u or v is going to be a unit vector. Okay, a unit vector say R has that the squared norm or that the 2 norm is equal to 1, right? Which means that the sum of j equals 1 to d of rj squared square root is equal to 1. Okay, so that's what it needs to be a unit vector. And this can only, it means every element has to be less than 1. And we can see right off the bat that this term has v has a quantity which is greater than 1 by itself. So it cannot possibly be a unit vector. So you don't even need to check that. I probably wouldn't give you something with this much calculation to check on the final, but on a homework, that probably would have been okay. But I need to square each of these. This is 0.25. This is 0. Or take the square root of each of these. No, you have to square them, sorry. So square of 4 is 0.16, right? So this one occurs twice. This one occurs, right, for this one, and 3 times. So 0.16 occurs 3 times. 0.1 squared is 0.01, and that occurs twice for this one here. Okay, so I'm going to add all of these things up. 0.25 times 2 plus 3 times 0.16 plus 2 times 0.01. Okay, this is 0.5 plus, let's see, 0.16 times 3 is going to be 0.48. And 2 times 0.1 is 0.01 is 0.02. And these add up to exactly 1. And the square root of 1 is equal to 1. So yes. So U is a unit vector, but not V. Okay. Yeah, I think to use actual decimals, I needed this many. That's why I had that many kind of dimensions, because I needed that to work out. Okay, calculate the dot product of U and V. The dot product of these guys is going to be just the sum, 0.5, 0.4, 0.4, 0.5. Here, well, let me do it this way. I'll write them underneath here, and then we'll add them up, right? 0.4, 0.4, 0.5, 0.1, 0.4, 0.1. Okay. So this is minus 0.5. This is minus 0.8. This is 0.4. This is minus 1, 3, 0.4, and minus 0.5. Okay, and if I add all of these guys up,
3 is 0.3 and 5 is 0.5.
Yeah, so it's, yeah, thanks. This is minus 0.5. This is 0.4. Oh, this is 0.3. Yes, 1. Okay, so 0.4 minus 0.8 minus 0.5. Let me try and see if I can add these things up on the spot. It's be more calculation I'd have you do on there, but I would just add these up. Add up. Okay. I'm going to go ahead and guess that this sum over j of all these terms is going to be equal to 0. I'm going to guess I set it up so that these cancel out. Okay, I add up all these terms, so it exactly equals to 0, and that means that yes, they are orthogonal. It's only orthogonal if it exactly equals to 0 here. So if the dot product is equal to 0, then they're orthogonal. It doesn't matter if one's much longer than the other one, they're still going to be orthogonal to each other. If it's not equal to 0, then they're not orthogonal. Okay, that's the only way orthogonality can work. Okay, so this with vectors, some key things are the dot product, unit vectors, and are they orthogonal? Those are kind of the most important simple concepts that we need a lot here. Okay, looks good. You can check at home if I added those up correctly, but I won't give you this much calculation on the final. Okay, here's a long one. Okay, consider a matrix n by 4. Okay, and each row represents a customer. There are n customers in the database. The first column is the age. Second column is the number of days since the customer is entering the database. Third column is the total cost of all purchases, and the last column is the total profits in dollars by the customer. Okay, I'm going to ask, are each of these reasonable or unreasonable? Okay, and I'm asking simple linear regression, k-means clustering, PCA, or linear classification. Okay, to try and predict if there's a profit or not. Okay, are these reasonable or are these unreasonable? Okay, so this is a little bit of a strange question, but you have to figure out what I'm trying to ask here. And there's this point I've kind of harped on a number of points in class, that if you're going to do a number of these things, if I have a matrix, let's say I have a matrix and I have A1, A2, up to AN, right? And each of these is a customer, and I want to take a distance between AI and AJ, and I want to use this as the Euclidean distance in between them. Yeah, so they don't have the same unit, so this distance itself does not make sense to do. So this does not make sense. Okay, it doesn't make sense to do this, to use this underlying distance here. Okay, so now we need to go back and say which one of these techniques was assuming that we could use this distance. And that was using the Euclidean distance was used specifically within clustering. Okay, so that one, this was unreasonable. Okay, it's unreasonable because we're using this Euclidean distance and this doesn't stand reason. Okay, to kind of compare quantities in this way, the age versus the total cost, because if I change the units from dollars to cents, it completely changes the distance without changing the meaning of what I'm trying to analyze here. Okay, PCA, we also is a way where we do this least projection error. This projection error also uses this notion of distance, onto a subspace of AI. It's minimizing this distance somehow, and this is this same thing again. So this one is also okay. No. So this one is also not good to use. Okay, these are not reasonable, but it turns out if I use simple linear regression without any regularizers, and I use linear classification without a regularizer or trying to minimize just the margin, these are going to be okay here. I'm not like violating anything specific with these two formulations. Okay, there are advanced versions we haven't talked about and I'm not doing that can run into some issues again, but at this point, these are all okay. Okay, so that's what I'm trying to ask here. This is a tough question to try and ask on a final exam because you have to kind of get what I'm trying to get at here, but this is a very important concept. So let me use this moment to kind of remind you of this again. Okay, great. That's question 8. Question 9. Okay, so consider a data set xy, where x, an n by 3 matrix, is decomposed into test and train set, x train, y train, assuming that x train is not just a subset of x, but also pads and prepends a column of all ones. Okay, then we build a linear classifier. Okay, we're building a linear classifier. This model should be in R4 because it prepended this offset term onto there. Okay, I think. Oh no, because y, yeah, okay, that should be in R4, I think. Okay, the remaining two remaining two testing data points. Okay, so now this test set only has 2 data points in it. Okay, so explain a mathematical expression to use the test data to estimate the generalization error. Right, that's the generalization error. Okay, this generalization error is how well it's going to do on new data, right? I want to predict how well it's going to do on data I haven't seen before, and that's what the test set is supposed to represent here. Okay, so one new data point arrives, x. How much squared error would we expect the model alpha to have compared to the known true data y? Okay, so I want to estimate this based on the test error. So what I want to do is I want to apply my model alpha onto 1x1, right? And I apply this model just with an offset, with a dot product. And I want to compare this to y1, but I want to expect the squared error, okay? So from data point x1, this is my estimation of the squared error. I've got this x1, which was held out of the data, right? This was held out, so I didn't train with this data point. And so now I want to say, well, what was the squared error on this data point? That's an estimation of it. I assume they're all IID from something unknown. So this is an independent sample under that assumption. And this is the squared error of one data point. But I've got 2 of them. So I want to add this together with alpha 1 x2 dot product y2 squared. Add these 2 together. So this is the sum of squared errors, but I want to predict it on one data point. So I want to divide by 2. Okay, so I'm going to add these 2 together, take the average. This is the average of the squared error on the 2 data points. And I'm getting a central limit theorem here again. So I'm getting a better estimate by averaging 2 things together. In general, I could be an average of n things together. In general, if I have k things, it's going to be sum over j equals 1 to k of alpha xj, right? This is the dot product minus yj squared, right? So this would be the general form over k data points, where I measure the error on each data point, and I'm going to take the average squared error of those, and that's my estimate of how well I'm going to do on some new data. Okay, this is one of the ways you use cross-validation. Okay, writing expressions I know are a little tougher in a Canvas quiz, so this might be, something like this would be tough for me to ask, because it's probably take you a long time to write this out. But this sort of question, this sort of information is important to get what's going on here. Okay. Consider a function fx with gradient, gradient f of x equals, at xy, is a gradient gives me a 2-dimensional vector, x minus 1 and 2y plus x. That's the gradient. So starting at a value x equals 1, y equals 2, and a learning rate of gamma equals 1, execute one step of gradient descent. Okay, so I want to understand that you can follow what is a gradient descent algorithm. Okay, so I need to do a couple things here. I need to evaluate the gradient. So I need to evaluate the gradient xy actually at these values, x equals 1, y equals 2. Okay, so the first step I need to be able to do is to evaluate this gradient at these values. And this is, at the first term is x minus 1. And so x equals 1. So 1 minus 1, okay, and 2y plus x. So that's going to be 2 times the value of y plus the value of x. That's 1. Okay, so this is conveniently 0, and 4 plus 1 is 5. Okay, so this is the gradient at this point. And now I need to do this update step. Okay, so I'm going to have that, let's say alpha is equal to x. Alpha is going to be equal to x equals 1, y equals 2. And I want to update alpha is equal to alpha plus the learning rate times the gradient of f of alpha, right? And we'd already calculated f of alpha. So this is going to be 1, 2 plus the learning rate times the gradient. The gradient was 0, 5. Oh, not plus the gradient, minus the gradient here. Okay. Should be minus. Okay, this should be, at after I do some step. Okay, and so this is equal to, and if you wrote this, it'd be good, but let's just write it out. So it's going to be 1 minus 1 times 0 is 1, is equal to 2 minus 1 times 5 is going to be minus 3. Okay, so this is one step of gradient descent. The learning rate of gamma equals 1, that goes in here, right? And then I've calculated this gradient at x equals 1 and y equals 2, and that gets plugged into here. Okay. Okay. Cool. So this is one step of gradient descent, and to run this, you just iterate this until it slows down, until the learning rate is, until the norm of the gradient is small or some number of steps. Okay, great. Okay, cool. So this is a fun question. Okay, consider running gradient descent with a fixed learning rate y. For each of the following, we plot the function value over 10 steps. Okay, the function is different each time. We should decide whether the learning rate is probably too high, too low, or too right. Am I going too rapidly down, too slow down, or it's going about right? Okay, and we should be able to get some understanding of this from just plotting this function value. Okay, and hopefully you plotted function values for some of the assignments and you have some sense of this. Okay, so let's look at this first one here. Okay, so for this first one, F1, the function value is going down by 1 every step. Okay, so is this going down too quickly, too slowly? Do you think we could go down faster? Yeah, we could probably go down faster at this rate. We're going down, we're not slowing down. We should be, ideally, right, you should have a function that's like this, and so it should, as you get, right, as you're going further down here, the function value should be kind of flattening off every step, right? So you're going to get a big jump, and then you get a smaller jump, and then a smaller jump. And if I look at these gaps should be getting smaller every time. So this one is probably, this first case here is probably just right here. It looks basically straight right there. It's not curving at all. So that means my steps are too small. So this is too low. Okay. Okay, let's look at this next one here. Now we're going from 10 or 100 to 50 to 75. Uh-oh, we went back up to 60 to 65 to 45 to 75 to 110 to 90 to 85 This one is doing something totally different. It looks like it's going down, but then it's going back up and down and up. It's something crazy like this. So this one is too high, right? Because I'm not consistently going down. I should be consistently going down, otherwise it's probably too high. Okay, the third one here, let's say, okay, I'm going down from 100 to 80 to 65 to 50 to 40 to 35 to 29, 28, 27.5, 27.3. This one looks pretty good. I'm kind of gradually coming in there, and it's kind of flattening out, right? This is kind of what you expect. So this one looks about right. This is about like what you expect to see. Okay, so let's look at this last one now. This last one's maybe a little bit trickier. 180, 60, 40, 20, 0, minus 20, minus 40, minus 60, minus 80, minus 100. Okay, so this one gets to the lowest function values. Okay, okay, but in this case, I'm still going down at a constant rate each step, right? So it's still dropping by 20 every time. So this is a different function, right? So this is supposed to say the function is different for every one of the sub questions. And so this one is, again, even though it gets kind of to very low values, this is just a different function that can get to very small values. So this one is also too low, actually. I want to make bigger steps so I can get down to minus 1,000 or whatever it's going to get to. Okay, so you don't know if the function values what the minimum is going to be. For here, the minimum was 27.3, it seems like, but in part D, it looks like the minimum was probably even smaller. Okay, so that's why I'm trying to ask it at this point. Okay. Question number 12. Okay, so this one is asking about the singular value decomposition for PCA and dimensional reduction and that sort of stuff. Okay, we've got a matrix A, which is 8 by 4, with these singular values. These are going to be the key here, the singular values here, which tells us kind of, remember, there's going to be these basis vectors, these are all orthogonal to each other. There's V4 also. If I try to draw that, it's going to be unintuitive, but kind of V3 is supposed to be coming out of the board, and then V4 is even orthogonal to that one. And these are telling me is how much they're scaling along these, right? The first one is the biggest, and the other ones are going to get smaller. Okay, so what is the rank of A? Okay, so first part A, the rank of A is going to be 4. One way of computing the rank is the number of non-zero singular values. In this case, it's 4, and that's full rank because that's the smallest one of the dimensions as well. Okay, so it can't be bigger than 4, and turns out it's exactly 4. Okay. Okay, what is A minus A2, where A2 is the best rank 2 approximation? Okay, so with the Frobenius norm here. The Frobenius norm, okay, remember the Frobenius norm is equal to, one way of writing this is J up to D of the singular value squared. So the squared Frobenius norm is the sum of the squared singular values, which in this case is 10 plus 5 plus 2 plus 1. Remember, I gave you the squared singular values, so I can just add these up. In this case, this is going to be 17. But in this question, I want to subtract out A2. A2 is just these guys, the first 2 singular values. That's going to be the Frobenius norm of that one. So what's left is going to be this. And so this value is going to be 3. Okay, I can also just write out that this is just the sum of the singular values starting at 2 plus 1, which is 3. So 2 plus 1. just these two guys here. Okay, so the norms of a matrix are easy to calculate once you have the singular values here. Okay, so remember this trick. There's a homework question on this, and a bunch of people did this in ways which were more complicated than were needed to be. If you have the singular values, you can just kind of write out the norms based on those. Okay, A minus A2, the spectral norm now. Now we're talking about the spectral norm. The spectral norm of A squared, this is just the top singular value. Okay, it's just the top one, which in this case is 10. But now I've gotten rid of the top two, right? So those dimensions have been flattened out, right? So I've taken these dimensions and I've kind of flattened them out. Remember, you can think of there as being some sort of elliptical structure. And what I've done is I've squashed it. I've squashed it down in this axis, and then I also squashed it down on this axis, but there was still something coming up out of the board, and that part is left. And I'm looking at the highest kind of singular value squared that is left. In that case, that's going to be exactly this guy. So this guy's going to be 2. So the first two singular values, these get mapped to 0 by doing this removal of A2, right? And then what's left is just the top singular value, which is left, top squared singular value left, which is a 2. Oh, and I also, let's see, I calculated these along the way. This was 10, and this was 17. Okay, great. So I can do those just from the singular values. That's a cool thing about that. And that helps you understand that that's where this captures, helps you understand the scale of this data in various ways. Okay. Next part here is talking about the right singular vectors. Okay, remember these were in this picture. They were telling me about the structure of the data. And now again, we're talking about the norm A times V2 squared. This is just identifying, I'm projecting the data onto this subspace defined by the second right singular vector and saying how much variation of the data is there in that subspace. That's what the squared norm is saying. And so I know the answer here is exactly going to be 5 coming from up here. So I'm just projecting onto the second right singular vector, looking at the variance there. That's what the second squared singular value is capturing. Okay? Okay, next. What is the dot product of V1 and V3? Well, these are orthogonal. These guys here, I have V2 or let's say V1 and then V3 is coming out of the board, and these are also supposed to be orthogonal, a bit hard to draw, but it's orthogonal with all the other ones. And if it's orthogonal, then this has to be equal to 0, right? Remember, that's what orthogonal vectors means. And if they're orthogonal, and so the dot product has to be equal to 0. Okay, and then finally, what is the norm of V4? And this is equal to 1, because they're all the right singular vectors are going to be so unit vectors, okay? So I know the norm of any of them is going to be 1. Okay, last part, write A1. Let A1 be the first row of A. Write A1 in the basis defined by the right singular vectors of A. Okay, when I do, so these right singular vectors gives me a new basis that tells me kind of the most obvious way the data is scaled. And I want to write it in that basis. So this is basically V transpose times A1. And it's going to give me a new kind of vector here. It's going to be another 4-dimensional vector. And the first term is going to be the dot product of V1 with A1. The second term is dot product with V2, A1. The third term is dot product of V3 with A1. The fourth term is dot product with V4 and A1. Okay, and that gives me a 4-dimensional vector. Oh, for 12E, is it 12E? Is it 17 or 18? This is oh, you're right. It should be 18. Good. This number up here, thank you. That should be 18. I added those up incorrectly. And good catch. All right. So this is when you say, yes, I made a mistake to see if you were paying attention. And so yes, you are paying attention. So that's great. Okay, so could we talk through C quickly one more time? Okay, yeah. So what's going on? Let's look at 12C. This is one of the questions. What is the spectral norm of A minus A2? A2 is the best rank 2 matrix of A. Okay, well, let me explain this in a different way. Okay, so A is going to be, one way I can write A is going to be a sum of J equals 1 up to 4. In this case, this is equal to D. D is equal to 4 of sigma J times Vj times Uj transposed. Okay, this is an outer product, right? This term here is an outer product, and it gives me an 8x4 matrix, as it turns out. Okay. Oh, I wrote those backwards. Let me fix this. This should be Vj Uj transpose. That's I wrote it the same way again. Okay, should be Uj Vj transpose here. Okay, and this should give me an outer product. Okay, and then A, the best rank 2 approximation of A, I can write this in a similar way, but I just stop J is equal to 1 only up to 2, only up to the rank I'm doing, and it's still going to be sigma J Uj Vj transpose. Okay, so then what this means is that A minus A2 is just going to be the tail. J is equal to 3 up to 4 of sigma J Uj Vj transpose. Okay, so this is this is the entity that we're interested in talking about, right? That's A minus A2. Okay, so we're looking at this entry, and it's just the sum of these two rank 1 outer product matrices, Uj Vj transpose, right? With J is equal to 3 and J is equal to 4. And we have their corresponding singular values, which scales them. Okay, so now these are kind of these orthogonal components here. And what the spectral norm is asking about here, the spectral norm, the 2 norm, is talking about what's the highest rank component of these, right? What we're going to have left is we're going to have some sort of matrix left here that's going to have V3 and V4. And these are going to be the only, let's say, sigma 3 times, these are going to be the only components left of this matrix, right? After we've factored out the part that was A2, we factored out those parts. We only have this component left, and what the spectral norm is asking for is was the any one direction which maximizes this, and that one direction is V3, right? And if you remember from this question, the norm of A in the direction V2 was squared norm of that was 5. Well, the squared norm in direction V3 is the one that maximizes it left, and that would have been 2 in that case, right? And that turns out that's what the spectral norm is. It's this guy right here. It's the leftover squared singular value that I haven't gotten rid of yet, the largest one that's left. Okay, great. Yeah. So it's, if you can see how these things fit together, you can answer a lot of questions about the matrix A based on its singular value decomposition. Okay, so that's what I'm aiming to get out of questions like this. Okay, this one is a lot of subparts. Probably, this would be a whole probably quarter of the final if I asked this question 12 on here, something like that. But there's a lot of different questions here, but they are asking lots of different questions about this and how you can realize information about a matrix just by its singular value decomposition. It really tells you a lot about its scale and different components. Okay. Okay, on to, this is a clustering question. I'm asking you the Vorni diagram of these set of points. And again, with clustering, these are often the sites. So I might have these sites, and I want to, and the Vorni diagram basically tells me how I assign stuff. If I have another data point, these data points, how do I assign them onto these sites here, right? And so I do that with the Vorni diagram where I assign every point. For instance, remember this point, I assign it onto the closest site. So I want to draw a Vorni diagram, and that basically is these bisectors between pairs of points that are closer to those points than anything else, right? And this one just asks you to draw this Vorni diagram here. And I've been drawing these for a while, so I've got them, a bit better at these things. Okay, so this should be the Vorni diagram here. So I want, this is, I like to answer questions like this when you can write on paper. And with a Canvas quiz, it'll be hard for me to answer a question like this. But this kind of helps you think through the assignment probabilities, right? So then what you should be thinking about, if I have a data point here, X, this tells me it's going to be assigned onto S5, right? So if I drew a picture of a Vorni diagram, it can tell you how do I assign one of these points, and this kind of gives you a sense of how to do that, right? The Vorni diagram tells you all that information. Okay, great. So that's the Vorni diagram. Let's see. Good. There's another clustering out question. What should I do if running Lloyd's algorithm for k-means clustering with k equals 2, right? So there are now two sites here, right? This is S1, this is S2. And you reach this sort of scenario, and the algorithm terminates, right? If I draw the Vorni diagram, it's just a bisector between these. Okay, I've identified these clusters, like all the points below the green line go to S2 and all the points above it go to S1. And so S1 is the average of those top points, and S2 is the average of the bottom points, right? So the algorithm actually terminates. It doesn't know how to update, right? But this doesn't seem like the right answer, right? I'd rather have an answer where I have, say, S1 here and S2 over here, right? That seems like a better answer here, right? Okay, so the answer is, so the question is, what should I do? What should I do if I run Lloyd's algorithm and I get here? Should I say, that's fine. I'm tired. This is question 14. I'm just going to stop, or should I do something here? And so the answer I'm looking for is that this can sometimes happen. And so what you should do is a random, restarts, okay, where I'm going to randomly reassign the centers in some other place, and hopefully that that it's going to give me a better answer here. For instance, even if I pick this one as S, here, let's do a different example. Let's say I picked these 2 points. Okay, even if I pick these 2 points as the cluster centers, well, what's going to happen is this new Vorni diagram is going to be here. So now after one step, this guy is going to be reassigned to the average. So this S1 will go to S1 here, and S2 will go to this spot, right? And then after this step, right, with these new centers, I'm going to get here, and now I've got a better situation. So this was a pretty unstable situation. If I reassign the centers to some random points, even though they both ended up in the same cluster, it kind of self-corrected. It was hard to get this split in this case, and so it ended up working okay. So I want to do a random restart is what I'm looking for here. Okay, but kind of understanding these two steps of Lloyd's algorithm, where is kind of the key thing to be looking here. One is, Sj is the average of cluster Xj, and B is cluster Xj is going to be equal to all points X such that phi of S of X is equal to Sj, right? So all the points that are closest to the jth center are going to be assigned to cluster X. And I just repeat these two steps, and that's what Lloyd's algorithm. You should understand what both of these steps do, and you should be able to answer questions about kind of this sort of clustering. And clustering is much broader, but this is what we focused on in this class. Okay. Question 15. Okay. This is about now classification question. Consider the following loss function. Okay, this is 1 minus e squared divided by 2, where for a data point xi, yi, and prediction function f, I think I generally use g here, right? So then zi is equal to yi times g of xi. Okay, predict how this might work within a gradient descent algorithm for classification. Okay, so the key thing here, again, if you can, to draw a picture. So I recommend having some scrap paper ready so you can draw a picture here. And so think of this zi function, and typically the idea is you have a 0 here, and this side is for kind of correctly classified. And so this side over here is incorrectly classified. Okay, so that's this idea of this zi equals yi times g of xi, that because yi is usually a -1 or a +1, and so if it gives me a function value which is negative, I multiply it by -1. It's correctly, then it should be a positive value, right? And it gives me in this pink side. So I typically want, what I would like is, remember, I would like this loss function that looks like this, right? This is this delta function here. I would like something like this. And now let's look at what this function is, right? Let's look at this loss function. Okay, so what is this doing? It's 1 minus z squared divided by 2. So let's pick some function values. If z is equal to 0, then it's going to be 1 minus 0 squared. So that's 1 divided by 2, have a value of 1/2. If z is equal to 1, right, if this is z of I equal to 1, it's going to be a value of 0. Okay, so far this is looking okay, right? If z is I is equal to 2, let's try 2, right? If it's a value of 2, well then 1 minus 2 is going to be -1 squared divided by 1/2 again. Oh, that looks kind of weird. Okay, let's try, try a value of -1. -1, 1 minus -1, it's -2 squared be a value of 4. It's going to be up here. Okay? And so what's going to happen is you're going to figure out that this is going to be a parabola. Oh yeah, it's a squared function here. So this is a parabola, and this looks kind of like this a parabolic function. Okay? And so what we can see is that this area over here, this part looks okay. Okay, it looks kind of okay approximation, but this part's not so bad. As I get better and better classified, I'm going to get more and more penalty, right? So this part is not so good. But on the other hand, it's going to be so differentiable. Okay, so I can take a gradient. So the gradient is good. So I can use it within gradient descent. I can take a gradient of it. Okay, it's convex. I can take any 2 points and draw the line that stays above. So this is going to be a convex function. Okay, so it's going to converge. So it can be used because it's differentiable. It will converge to a global min because it's a convex function, but will penalize well classified points, right? So this area over here is penalizing well classified points. So, these are kind of the 3 points I'd want to cover. How exactly I would grade this question is kind of tricky, but this is an actual exam question. But probably what would happen is that you'd find a decision boundary near all the points, kind of like regression. It's going to kind of look like regression. It's going to have a decision boundary near all points. Okay, so probably what would happen is if I had some positive points up here and some negative points like this, the optimal classifier would look like this, but the one I would find would probably look something like this instead, right? Where this is, it's still probably actually classifying them all correctly, at least in this example, but it's not going to generalize well to new data. If I have a new data point over here, I'd guess it's probably positive, but I would have gotten it wrong, so it won't generalize as well. And it could be that I kind of misclassify even some of the points in the training set when I didn't need to because of this. Okay, so whether or not you get this very last part here, kind of the lesson here is if you have something about a loss function, draw a picture that looks like this, and then talk through these kind of these 3 points. Is it differentiable, right? Will it converge to a global minimum? It has to do with the convex. And then, but will it penalize points in the right way? And then it has to do with, well, what's going on in this part of the space over here. So those are kind of the 3 things you should be looking at. Or is it always above this curve? Sometimes you always want it so it's always above the delta function. That's what I asked for on the homework. That's a little bit less important. Okay, but that's often what people want, something like that. Like a hinge loss instead would satisfy that. Okay. Okay, the final question, another classification question. This one asks about k-nearest neighbors, one of these other classifiers I talked about. Here I'm giving you one-dimensional data, and there's no picture, but you should draw a picture here. Let me draw. Okay, and it's a one-dimensional question, right? So R1, I try to keep it simple. And I have points, let's say they go from, let me put 0 over here, goes from, actually, let me move 0 a little bit further, 0 up to something like 9. Okay, let's try and draw these. All the positive points. Okay, these are going to be x equals 0. This is x1. X equals 2. This is x3. X equals 4. That's at value 4. X7 is at 8. Right, this is 8, 7, 6, 5, 4, 3, 2, 1, 0, minus 1. Okay. Now let's draw the negative points. Okay, so x2 is at 1. X5 is at 6. X6 is at 7. And X8 is going to be at 9. Okay, good. So I've drawn this picture, and this is what's going on. The blue boxes are negative points. The red dots are positive points here. And now I want to predict a K-9 classifier with K equals 3 on the following queries. Okay, this isn't, I can't separate these with a linear separator, but a K-9 classifier doesn't need it to be linearly separated. And I'm going to have a, let's see, I'm going to use K equals 3 points, and for x equals 3, let's do this first. So x equals 3. Okay, x3, and I want to find the 3 nearest neighbors. The 3 nearest neighbors are these guys, and I have 2 pluses and 1 negative, so plus 1. Okay. Okay, the next query is going to be x equals 9. Okay, and that matches one of the data points. And I want to find the 3 closest ones. That's 2 negatives and 1 positive, right? A negative, a positive. So this is a minus 1. It votes. It counts how many are in this, and then 3 nearest neighbors, and see which is more. And then the final question is with x equals minus 1. That gives me a value out here. This is going to be x equals minus 1, and the 3 nearest neighbors look like this. And again, there are 2 positives, so this is the plus 1. These are positive. Okay, so that's how the K nearest neighbor classifier works. Okay. Yeah, so that covers this the practice exam. We went through that, and I think this should definitely be longer and probably in some places definitely more tricky than I plan to ask on the final. So there's one question here. So is there a way to decide if you have points on both sides of R1? Yeah, so in this case, right, if for this example here, I've got points on both sides, right? So this is the query. This is the new point. And so I've got points x2, x3, and x4. Those are the closest. Those are the closest points are on both sides. Now, if I had a tie, right, if I pick something where the third closest point was a tie between 2 things, then that would be tricky. I would try and set the question up so I didn't have that case, and that's what I did here. If x equals 5, for instance, so you're asking for this question if the query is here, and then, well, this is okay because I've only got the 3 closest points are x5 and x6 and x4, because there wasn't anything at x3. That was a test point, not a training point. Yeah, but this could definitely happen. Let's say I picked a point right here at 7.5. Then x5 and x8 are the same. But in this case, 3 out of 4, so it was still okay. So even if I picked either x5 or x8, they're both negative, so it's still fine. But yeah, if they're ties, then becomes trickier. I won't ask you that question on the final. Yeah. So okay, great. So we finished everything I planned to go through. I'm happy to take any other questions. I can stay until 4 o'clock, another 15 or so minutes. But I think this gave a pretty good coverage of what we did over the semester. And if you understood all this stuff, you should be pretty good on the final. If you followed along, even if you need me to explain some of the trickier parts, I think you should be pretty good shape on the final. Might cover slightly different stuff. This is a sampling of the questions, but try to give a sense of hits all the most of the main points we did over the course. And I'll try and have similar bounds in the final, but this one took me, let's see, we started at about 2:15, so about an hour and a half to cover all this stuff. I expect I'll be able to finish the final in under half an hour, right? It's me, the instructor, you guys, you might be faster, but I don't expect you to be, a little bit slower than me. But this one definitely took longer to go through and work all this stuff out. So I recommend making a good cheat sheet for the final. Yeah, so I'm thinking, well, any suggestion how I'll follow up the review for saying, yeah. So I recommend you kind of get 4 sheets of paper, and I think what we'll do is actually, I said right now it says out of 5 points. I'll probably make it so it's a sliding scale. So you can actually get up to 6 points if this looks really complete and good. But if you just turn in some nonsense, you might only get 1 or 2 points. So please make a detailed study sheet. I really think this helps you kind of focus on what are the most important things. And it's fine if you want to do it on a computer and copy and paste stuff and put it in there, that's totally fine. If you want to write it out by hand, that's fine. But just kind of review and reread the things that you pick out you think are most important. And so by selecting those things and rereading those key things, if you get confused about something, then you can come ask. Yeah, would you be docked if you have less than 4 sheets? If I won't take away any credit, the credit you get for that are going to be bonus points, but you may not get the full 5 or 6 points if it looks very sparse. If it's 2 or 3 pages and there's a lot of stuff on there, then that's probably fine. Yeah, but I'll probably get 6 points for the very best, and probably 5 points if it looks like you made a good effort, and probably less bonus points if you made a less good effort for that. But it'll still be 2 or 3 to do something. Yeah, I will have my office hours Thursday at 10. I'll still have my last office hours at the regular time this week. I think those are probably the last ones. Hassan's would have been today, but those would be the last office hours. And you can ask me any questions then or now, and I'm pretty good at responding over Canvas or email, so you can also ask for clarification on that stuff. Oh, and will the final be multiple? Yeah. Oh, I missed this one. Will the final be multiple choice for the most part? So yeah. So my plan, I said at the very beginning for this one is that the final will be it's going to be, I'm going to aim for more questions, but simpler things like multiple choice or true false. But it's not going to be everything. There's going to be some some might be some fill in the blanks or some answer stuff. I'll try and mix it up some, but I'd rather have more questions so each one is worth less points, so that if you miss something, it's not as catastrophic. Okay, so that's the goal. But it should be kind of like the quizzes you saw. Think of about 4 quizzes stuck together. So that's the right way of thinking about it. And I'll try and aim for the ones that had more, but simpler questions. They can cover more topics because there are kind of effectively 6 quizzes this semester. Yeah. All right. So if no one else has any questions, good luck everyone on the final. Enjoyed teaching the class. Those of you who are showing up, thanks. It's better than lecturing into the void and hoping someone watches it later. So hope everyone stays safe. And if you want to take a class from me next semester, I'm teaching this ethics for data science class, and I'll try and accommodate whoever wants to take the class. So, all right, great.
Thank you.
Yeah. So see Hassan, thanks for logging on.
You're welcome.
And helping answer the chat questions. Or the one chat question that kept coming up about, is this being recorded? Yeah.
See you.